This is Unit 2, Section 2.4, looking at Pythagorean Theorem and the Converse. So we've just taken our quiz and now we're looking at moving into our second half of this unit where we've practiced simplifying radicals and now we're going to apply that in a couple different applications looking at Pythagorean Theorem, which should be a review, and then we have two types of special right triangles. So what we're going to look here is at the Pythagorean Theorem to begin with. So the reasons that we would use this theorem, and sometimes this might be maybe what your parents, the only thing that they remember from geometry, which is crazy, but they'll remember this idea that when we want to find the missing lengths of a triangle, and this specifically has to be a right triangle, we can use the Pythagorean theorem. Sides A and B are called the legs, and side C is called the hypotenuse. So A is a leg, B is a leg, and C is the hypotenuse, which I abbreviate HYP. For any right triangle, we can take the leg squared plus the leg squared, and that will always equal the hypotenuse squared. Okay? Otherwise written, if we have the picture set up this way, we can use a squared plus b squared equals c squared, but only because a and b are the legs. C always has to be the hypotenuse. One of the things that we're going to come across are, I like to use Pythagorean triples, and these are quick numbers that will work for Pythagorean theorem every time. So a Pythagorean triple is three positive integers which make the Pythagorean theorem true, and we call those triples. So for instance, if I took 3 squared plus 4 squared, it equals 5 squared. 9 plus 16 is 25. So this is called a triple. And so I'll use this one frequently because it's quick for me to come up with a special right or a right triangle that has sides 3, 4, and 5 and talk about it. Another one of my favorites is 5, 12, and 13. This is another triple that we use pretty frequently. What's interesting about this is that because this holds true here, it will hold true for any other multiple. So if I took this and multiplied by 2, and multiplied by 2, and multiplied by 2, this would also be a Pythagorean triple. We'll start making a list, so if you come across one in the homework or as we go and continue on the notes, we'll make a list that I want these to be something that we can reference and quickly see, so as we start applying further into our units with perimeter, area, volume, we see and recognize these triples. So if I see 3, 4, I know the hypotenuse is 5. And so it's supposed to be a quicker way of seeing kind of that pattern. So our first examples are applying the Pythagorean theorem to find a missing length. And so each one of these, notice, is a right triangle. We have that right angle indicator for those perpendicular sides here, making that right angle. So if those weren't there, we couldn't apply the Pythagorean theorem. It only works for right triangles. So here I have a leg, and a hypotenuse. So I'm going to set up a squared plus b squared, and then I have my unknown. So in my calculator, I'm going to write out what is 8 squared plus 13 squared. I'm going to change my view to the scientific so I can get squared. So I'm going to do 8 squared plus 13 squared, and I get 233. Okay, and that's what x squared equals. And this is where I need not just what x squared is, but what x is. So our inverse to squaring something is square rooting. And if I do it to one side, we do it to the other. So I put in here, square root of x squared cancels. That's where anything squaring a square root comes out. And then square root of 233, and this says give both in simplified radical form, okay? and rounded to this nearest tenth. So if I bring down 233, I want to see if I can simplify that. Okay, and I can't. So that's as simplified as it gets. And then on my calculator, I'm going to check square root, and I get 15.3 because rounding to the nearest tenth, that 6 will bump up my tenths. So there's my approximation. And the radical here, 233, is as simplified as I can get. All right, on number 2. Okay, across from 90, here's my hypotenuse. So sometimes I might label that one first. That way I know it doesn't matter how I label A and B, but C has to be across. In fact, sometimes I see this as like an arrow where it's like pointing at C. So I can set up 27 squared plus 22 squared equals x squared. I'm looking for C again. So in my calculator, 27 squared plus 22 squared equals 1213. So I have 1213 equals x squared. Simplify by taking the square root of both sides, leaving me with x, and here's my radical. And then on my calculator, I will take the square root of that to get my approximation rounded to the nearest tenth, 34.8. And that would be my approximately x. So here's my rounded to the nearest tenth, here's my radical. On number 3, we have C is across from the right angle, so here's C, A and B. So now I have 7 squared plus x squared equals 9 squared. And notice now I'm not looking for the hypotenuse, so it's not always going to be what we're looking for here. Now I'm looking for this shorter leg here. So what I'm going to do is take 9 squared and I'm going to subtract 7 squared because I want to move that over to get x squared by itself. So in my calculator, I'm going to do 9 squared, the hypotenuse, minus now the 7 squared, 49, and I get 32. So now I have 32 here, and then I'm going to simplify. Take the square root of both sides to cancel out. And square root of 32, a 16 can come out, and the square root of 16 is 4. Radical 2 as my simplified radical form. And my calculator approximation, take the square root, is 5.7. So it's approximately 5.7. So when we're simplifying this, I did break this up into the radical 16, radical 2. Square root of 16 is 4. Square root of 2 is, we don't know, so it stays under. It's the leftovers. If you have a TI 36 or better, it will simplify that radical for you quickly. And because we've already quizzed over the simplifying radicals, it's okay to do this a little bit faster, knowing what your calculator's doing. So kind of keep that in mind. This calculator on my Mac won't simplify the radical. I have to do that either by splitting it up, or I have the TI 36, but again, I can't show that on my screen right now. On number 4, we have A, B, and C is always across from 90. So we can check A squared plus B squared, hello 2, equals C squared. Okay, on my calculator, I can do 5 squared plus 12 squared equals 169. So here I get 169 equals x squared. Undo the squaring by square root both sides, and I get x here, and 169 is 13. So in this case, I don't need an approximation because 13 is the exact answer, which is also another triple. That's my 5, 12, 13 triple. So if we had seen that right away, we could have immediately said, oh, that's 13 without doing this process. So there are a couple triples that we're going to use so frequently that you might catch on to that pattern quickly or go, oh, I already knew that one when you solve. Are there any of these others triples As soon as they have a decimal or a radical left over, they're not going to be a triple. This was our first other triple. On number 5, okay, across from 90 here, we have our C, and then A and B. So we have x squared plus 19.1 squared equals C squared, 30.5 squared. I'm going to take 30.5 squared and subtract the 19.1 squared to get x squared by itself. So 30.5 squared minus the 19.1, so I can move that to the other side, squared equals 565.44. All right, so if I take the square root of both sides to get x by itself, canceling, I kind of like how that canceled out, leaving me with x, and we get an approximation here of square root 23.8. I'm going to use that 7 to round up here. And that's approximately. I could have told right away that this wasn't going to be one of my triples because they already had decimals here. And another decimal, still not a triple. Our last one is kind of an application because right now we have this triangle, which is not a right triangle. But if we draw in this line they've given us where x is, now we do have a right triangle. So we have x here. We know these two markers are the same, giving us 24 and 24. And if we split this in half, 11 and 11 would make that 22. So now I have my A here for x, my B for 11, and across from 90 is my C. So I could set this up to solve as x squared plus 11 squared equals 24 squared. All right, so again, because one of my sides is unknown in my calculator, I'm going to take the larger 24 squared and then subtract the 11 squared so that it's on the same side. So now I get x squared equals 455 and simplify by taking the square root. I kind of like this. Square root cancels out to get x. Do it to one side, do it to the other. So here's my radical. And if I simplify to get the decimal approximation, I can say it's approximately, square root 21.3 is the length of this. So about 21.3 here. I had 11, 24. As soon as I have a decimal, not a triple. All right, let's look at a word problem. This is a classic one where for Pythagorean theorem, I don't know why we would necessarily need to know how high up the wall we reach without just leaning the ladder up. But this seems to be one that shows up a lot on standardized tests. So ACT, Kansas Math Assessment, MAP testing, where they would say you place a ladder against a wall. And in this case, they're telling us how long this ladder is. This is a 10-foot ladder. So we can, if we're holding this, it reaches 10 feet. If the base of the ladder, here's the base, is placed 3 feet from the wall. So we know from the wall, this is 3 feet. How high up the wall does the ladder reach? Okay, so this is X. If you were to ask somebody younger, or maybe your first time kind of thinking about this, you would think, oh, a 10-foot ladder should be able to reach 10 feet up. But the thing about a ladder is that you don't place it up against the wall because as soon as you start to climb it, you would fall backwards. So it doesn't reach quite 10 feet. That's going to be the longest side. But we can set up, assuming that this wall is perpendicular to the floor, the Pythagorean theorem to check and see how high it actually reaches. So on my calculator, I'll do the 10 squared. And because I'm looking for a side, I'm going to subtract the 3 squared, which gives me 91. So I have x squared equals 91. Square root both sides. And I get x equals, square root of 91. And square root approximately 9.5. Okay, so if I were to look at answers for a real world problem, it's unlikely that I'm going to report radical 91 feet. I wouldn't say, oh, this ladder reaches there. I would say, oh, this ladder reaches about 9.5 feet up. It's not quite, it's a little bit actually higher than that, but that's going to be pretty close to negligible at the end there. So when we're answering real world problems, we're typically going to do with the approximation because our rulers are tape measures. They're not going to measure in radical 91s here. So that would typically be out just for context. But this is the exact answer. This is still an approximation. So it just says how high up does the ladder reach? We have our sketch, and either one of those would be fine. This approximation makes more sense as far as the context of an actual conversation. The next thing that we're going to look into, the second part of today, is looking at the converse. And so this part might be new, where we're going to actually go backwards and say, if we know that a squared plus b squared equals c squared, if we know this is true, then the triangle is a right triangle. So this goes the opposite way. So if I just have any old triangle and I don't know if this is a right angle, but I have the 3 side lengths, I can check. If a squared plus b squared equals c squared, that has to be true only for right triangles. So it tells me it's a right triangle. So what if it's not? What if a squared plus b squared is related to some c squared, but maybe it's too big? Maybe c squared is stretched out further. Okay? If this is not 90 because this is too big to make it 90, this is stretching it out. What I do is I look at C and I know, hey, that's too big for a right triangle. It was bigger than what we were expecting. This is going to make it an obtuse triangle because what's going to happen is this angle is going to get pushed out to accommodate that longer C length. Okay? We can also go the other way. If a squared plus b squared doesn't equal c squared, and in fact, c squared is too small to make it a right triangle, kind of like the Goldilocks rule here, this would make it an acute triangle. And so what this would look like is, okay, I'm not sure what this is, but I do know that it's not a right triangle because C is too small. Do you see that now this is becoming an acute angle? That's what makes it an acute triangle. We always look for the C squared. Is it just right? Too big or too small? That's why I kind of call it the Goldilocks rule. So this is a way that we can use the Pythagorean theorem, but in the opposite direction, which is why we call it the converse. To now apply something that only works with right triangles and look to see if we can classify any triangle based on this property. The last thing here is that there are certain lengths that will form a triangle. If I was looking at a triangle that had lengths 1, 1, and 100, okay, I would have this long length of 100, and then I would have something here that's 1 and something here that's 1. This would never form a triangle because these pieces would never be able to touch each other. So it would be like little flappers in oh gosh, what is that called? The game, pinball game. It kind of looks like flappers. They would never actually make a triangle. So there's a rule that we'll follow in order to check to see. If I just pick any 3 lengths, how do I know it forms a triangle? So in order to form a triangle, the sum of the 2 shorter sides, that's A and B, must be larger, so greater than the third side. So the rule is if I just check A plus B, if I check the 2 smaller sides, they have to be greater than C to form a triangle. So if I'm given any 3 lengths, so instead of here, I could have checked, oh, 1 plus 1, is that bigger than 100? No, 2 is not bigger than 100. This doesn't form a triangle. But if I did 50 plus 51, is this bigger than 100? 50 and 51 is 101. This would form a triangle, 50, 51, and 100. And we could then check the converse to see what kind of triangle it was. That's our last examples here. So we have 2 steps that we're going to take. It says first, determine if these 3 side lengths could form a triangle. Since we don't have a picture, we need to make sure that they first form a triangle to begin with. If they do, then let's go ahead and classify further as acute, right, or obtuse using the Pythagorean theorem. All right, so the first thing we check is, does it form a triangle? That is, A plus B has to be bigger than C. Then we check to see if it's acute, right, or obtuse. That's where we square it. So the first thing I'm checking, does it form a triangle? So 3 plus 7, is that bigger than 9? Is 10 bigger than 9? We have a triangle. What kind of triangle? So now I'm going to square the 3, square the 7, and compare it to 9 squared. So 3 squared plus 7 squared, 3 squared plus 7 squared gives me 58. 9 squared, I get 81. And so 81. It's not the same, so it's not just right. 81 is too big, which would classify it as an obtuse triangle. So does it form a triangle? Yes. What kind? An obtuse triangle. The first ones we don't square, the second ones we square and compare. On number 2, we'll check, does it form a triangle? We take the 2 smaller and make sure it's bigger than the third. 20 and 21 is 41, bigger than 29. So then we square each piece and compare it to the last piece. We want to know, is this too big, too small, or just right to this sum? So on our calculator, we'll check 20 squared plus 21 squared. We get 841, okay? And we want to compare it to 29 squared, which is also 841. So when I compare 841 to 841, it is just right, telling me this is a right triangle. On number 3, let's check 4, 11, and 16. Notice that I've taken off some of that direction. We want to check. First, is 4 plus 11 bigger than 16? Okay, so 4 plus 11 is 15. 15 is not bigger than 16. So immediately we can say not a triangle. Okay, so we don't even need to do part B because it's not a triangle to begin with. So we move on. So on number 4, check to see if it's a triangle. 17 plus 17, is that bigger than 22? 34 is bigger than 22. So we do want to classify this, and that's where we start to square it and compare it to the 22 squared. So I'm going to put in my calculator 17 squared plus 17 squared, and we get 578 here. And we want to compare to 22 squared, 484. Okay, so this is not just right because they didn't equal each other. In fact, this is too small, which tells us this is an acute triangle. So again, I circle this just to indicate that's what I'm comparing. I want to know, is C squared just right? It's right. If it's too small, it's acute. Too big, it's obtuse. On number 5, we'll check. First thing, do we have a triangle? Is 18 plus 30? Uh-oh, I went out of order. We need the 2 smaller ones here. So I'm going to change that. We have to make sure they didn't give us those in order from largest to smallest, or smallest to largest. So I'm going to check, is 18 plus 24 bigger than 30? Okay, we have 30, yep, 42 is bigger than 30. So let's see what kind of triangle we have. 18 squared, 24 squared, and I want to see how does it compare to 30 squared. Back to my calculator, 18 squared plus 24 squared is 900. Okay. And compared to 30 squared, also 900. This is equal. That has to be a right triangle. On number 6, part A, we're going to check, do we have a triangle? 8 plus, okay, there's my smaller medium, and compare, is that bigger than the other one? 8 plus 15 is 23, so that's not going to work out because that's going to be equal to, not greater than. So immediately, not a triangle. That will form just a straight line where that 23 here and the 8 and the 15 would just end up matching right here. They wouldn't pop up and make it a triangle. On 7, we'll check 31. Okay, that's in order, plus 35. Make sure that's greater than 39. So that's 66, bigger than 39. So let's see what kind of triangle it is. 31 squared plus 35 squared, and we want to compare to 39 squared. On my calculator, 31 squared plus 35 squared, since they're on the same side there, 2,186. And 39 squared is 1,521. Okay, so looking at this one, it's not equal. In fact, C was too small to make it a right triangle. So because it's too small, that tells us this is an acute triangle. And on our last one, okay, part A, check to see if we have a triangle. 11, 19 are two smaller lengths. Is that bigger than 28? So 11 plus 19, okay, that's 30. 30 is bigger than 28. So part 2, let's see what kind of triangle we have that's formed here. On my calculator, 11 squared plus 19 squared, 482. And I want to compare it to 28 squared, 784. All right, so when I compare, this is not just right. It's not a right triangle. C was too big. And because it was too big, this is now going to be an obtuse triangle. So our goal today was to review Pythagorean theorem and how we set those up to find one missing side length. And then the second part was, if I give you any 3 side lengths, can we determine, is it a triangle? And if so, what kind? Acute, obtuse, or right? So we used that quite a bit today. On your practice, let me know if you have any questions, and I hope you have a good day.